Hello, and welcome. There's nothing you need to do right now. Nothing to follow closely, nothing to remember, nothing to hold on to. You can let your shoulders drop, let the weight of the day settle down out of your arms and your hands, and let the bed or the chair take all of it for a while. If your eyes are still open, you can let them close whenever they'd like to. The words will keep going softly in the background, and you don't have to keep up with them. They're just here to keep you company as you drift down towards sleep. Tonight we're going to spend some slow, unhurried time with one quiet idea, a small and rather beautiful thing that a telescope found out in the dark, very far away. We'll wander around it gently, the way you might wander through a museum late in the evening when almost everyone has gone home, pausing at whatever catches the eye, in no rush at all to reach the end. There's no test at the end of this. There's no surprise waiting to wake you up. The whole point is the opposite of that. The whole point is for your mind to grow soft and slow and finally let go. So let me tell you, in the gentlest way I can, about a faint little mark that appeared on a chart. Far out in space, beyond the moon, beyond the planets, beyond almost everything you could point to in the night sky, there is a telescope. It's called the James Webb Space Telescope, and we'll come back to it many times tonight, slowly, because it's a patient and rather lovely machine. For now, all you need to know is that it sits very still in the cold and the dark, and it gathers light. That's really all it does. It collects light that has been traveling for an unimaginably long time, and it spreads that light out, the way a drop of rain can spread sunlight into a soft band of color, and it lets us look carefully at the bands and the lines hidden inside. And one day, in among all that gathered light, there was a small spike, a thin little line standing up where the scientists hadn't quite expected to find one. Nothing dramatic to look at. If you saw it on a screen, it would be a modest peak, a gentle rise, the sort of thing you might walk past without noticing. But to the people who had been waiting for 50 years for something exactly like it, that quiet little line meant a very great deal. Let me tell you what it was, slowly, with no hurry at all. The line was made by helium. Helium is the second simplest thing in the whole universe, the second entry on that long list of elements you may half remember from a classroom long ago, the periodic table, with hydrogen sitting right at the front and helium just behind it. Helium is the gas that lifts a party balloon and makes a voice go high and silly. It's light, it's gentle, it's everywhere. There's nothing frightening about helium, and yet a particular kind of glow from helium, a very specific shade of light it can give off when it's heated in a very particular way, turned out to be one of the most quietly meaningful things a telescope has ever caught. Because here is the thing about that little spike of helium light. To make it, you need warmth. Not the ordinary warmth of a fire or a stove or even the surface of our own sun, but a warmth so deep and so fierce that almost nothing in the universe today can produce it cleanly. The helium had been heated until it had let go of both of the tiny particles, the electrons, that normally circle around it. Stripped bare, you might say, down to its core. And to strip helium bare like that, twice over, you need light that carries an enormous amount of energy, the kind of light that pours off a surface hotter than 100,000 degrees. Sit with that number for a moment, softly, without straining at it. The surface of our sun, which is already far hotter than anything we could ever stand near, is around 6,000 degrees. The thing that made this little line of light was something like 17 times hotter than that. A surface so hot it's almost outside our ordinary imagining, and whatever it was glowing out there, gently and steadily, in a small pocket of space, sending that signal across the whole long width of the universe, so that one quiet machine could catch it billions of years later. That alone would be a curious little fact to drift off to. But there was something else about the signal, something even gentler and even stranger. And it's this second thing that made the waiting scientists lean in. The light was alone. Let me explain what I mean by that, slowly. When we look at the light from a star, or from a cloud of glowing gas, or from a galaxy, we almost never see just one kind of glow. We see a whole crowd of them, a little signature from carbon, a little signature from oxygen, from nitrogen, from iron. These are the fingerprints of all the heavier ingredients that get baked inside stars over the ages and then scattered out into space when those stars come to the end of their lives. Every cloud, every star, every galaxy we have ever studied carries at least a faint trace of these ingredients. Every single one. The universe has been quietly recycling itself for over 13 billion years, and that recycling leaves its marks everywhere, like the faint smell of wood smoke that lingers in a room long after the fire has gone out. But this little signal had none of that. The helium was glowing, and all the other fingerprints, the carbon and the oxygen and the iron, were simply absent. Not faint, not hidden under noise, just not there. As though this light had come from a place where no star had ever lived and died, where nothing heavier than helium had ever been made, where the long list of elements still had only its first two entries and nothing more, and that combination, a fierce glow of helium together with a clean, empty silence where all the heavier things should be, had never been seen before, not in any galaxy, not in any cloud, not anywhere, at any distance, in all the years that people had been gathering light from the sky. Until, very quietly, it was. Now you don't need to hold all of that. Let it wash past you. The shape of it is enough. A small bright line, very warm, very clean, very far away. A signal that looked, to the people who had been hoping for it, exactly like a message from the very beginning of things. Let's drift on gently now and talk about where it came from. The little signal was found near a galaxy. The galaxy has a name that sounds more like a code than a name, GNZ11, and you don't need to remember it. It's just a label, a tag that astronomers gave to one faraway smudge of light so they could talk about it without confusion. But this particular smudge is special because it is one of the most distant galaxies we have ever managed to study at all. When astronomers talk about how far away something is, out at these enormous distances, they often talk about how long its light has been traveling, and the light from this galaxy has been on the move for a very, very long time. Roughly 13,400 million years. The light left its source when the universe was young, less than 3% of its current age, and it has been traveling ever since through the slow and patient expansion of space, drifting and stretching and growing fainter, all that time until at last it arrived at a small mirror floating in the dark and was gathered in. Think, very softly, about what the universe was like when that light first set out. There were no planets like ours, no oceans, no mountains. The sun did not exist, nor did the cloud of gas that would one day become the sun. The Earth was not even a possibility yet. There was only the early cosmos, cooling slowly from its first warmth, gathering itself into the very first faint structures, mostly dark, mostly simple, mostly waiting. And from that early, quiet, waiting universe, a little bit of light slipped free and began its long journey toward a future it could not have, imagined toward a small machine built by creatures who would not appear for another 13 billion years. There's something soothing in that, I think. The patience of it. The light didn't hurry. It had nowhere it needed to be. It simply traveled at the only speed light knows, while galaxies formed and stars were born and died, and worlds came together out of dust. And at the end of all that, it arrived, gently, exactly where it needed to be. Now, I should be honest with you, in a quiet way, about what we actually see when we look at this galaxy. It would be lovely to imagine a grand spiral, a great glowing pinwheel of stars, the kind of picture you might find on a postcard, but that isn't what the telescope sees at all. At this enormous distance, the galaxy is only a handful of specks of light, smeared softly across a detector, so faint and so far that without this particular telescope, it would be entirely invisible. We don't really see its shape. We see its light spread out into its colors, into that gentle band of bright and dim that tells us, in its own quiet language, what the light is made of and how warm its source must have been. And it was right there, at the very edge of that faraway smudge, not inside the galaxy but just beside it, that the little helium signal was found. Out on the outskirts, in a quiet pocket of space, just off to the side, where you might least expect anything important to be hiding. That detail is worth lingering on for a moment, softly, because it's a little surprising in a gentle way. Stars usually form inside galaxies, down in the dense, gathered heart of things, where gravity has pulled enough material together to make new stars. The outskirts are emptier, thinner, quieter, and yet here was this signal, off to the side, in a place that seemed too lonely for star-making, as though a small reservoir of the universe's original material had been sitting out there, untouched, while everything around it had already begun to change. A little pocket that the long recycling of the cosmos had somehow passed by and left alone. The gentlest explanation, the one most of the scientists settled on, is that this really was a pocket of original, untouched gas, a small cloud of nothing but hydrogen and helium, the simple stuff left over from the very beginning that by some quiet accident of geometry had never been reached by the debris of earlier stars. It just sat there, clean and undisturbed, for hundreds of millions of years, while the rest of the universe busied itself growing more complicated. And then, at some point, something stirred it, and it began at last to make stars of its own. If that's true, then what we're looking at is a rather tender thing, a bit of the universe's original material, caught right at the moment it finally began to do what all the rest of the universe had done long before, to gather itself together and light up. The very beginning, happening late, in a quiet corner where one careful machine happened to be looking. And there's one more small surprise near this galaxy, which I'll mention softly and then let go of for now. This little smudge, this early galaxy from the young universe, seems to hold at its center a black hole, and not a small one, a large one, larger than we would easily expect to find so early in the story of things. We'll come back to it later, gently, because it ties into the rest of tonight's wandering. But for now you can simply let it sit there in the back of your mind, a heavy quiet thing at the heart of a faraway galaxy, doing its slow work in the dark. Let's drift on. I want to tell you a little more about the helium and about what it really takes to make light glow the way this light glowed. But I'll keep it soft, and you can let the details slip past if they want to. The feeling of it is what matters, not the holding of it. Helium, as I said, is a very simple thing. Picture it, if you like, as a tiny center with two even tinier particles drifting around it, like two small moons circling a little world. Those drifting particles are the electrons. In its ordinary peaceful state, helium keeps both of them. To pull one of them away, you have to give the helium a real jolt of energy, a push of light strong enough to knock that electron loose. That already takes the kind of light that lives beyond the colors we can see. In the part of the rainbow we call ultraviolet, the same invisible light that can give skin a sunburn on a bright day. So even pulling away one electron means something fairly fierce is happening. But the helium in this faraway signal had lost both of its electrons. Both of them gone, stripped away, leaving just the bare little center behind. And to do that, you need light that is far stronger still. You need something genuinely deeply hot. Not warm, not bright, but hot in a way that very few things in the whole universe can manage, even now. The kind of heat that only the most extreme and most enormous stars can produce. And so, in a roundabout, quiet way, that one little line of helium light is also a thermometer. It tells us, without anyone having to go and measure it, that whatever made it was burning at a temperature beyond 100,000 degrees. Something was out there, in that lonely pocket of space, glowing with a heat we can barely picture, and it left us a small, faithful note about itself, written in light, and the note traveled for 13 billion years to reach us. and it said simply, I was very, very hot. Now let me tell you about that other word, the one the scientists use. That sounds a little odd at first. They call all the heavier ingredients, everything past hydrogen and helium, by a single name. They call them metals. It's a funny old habit, and I find it rather endearing. When an astronomer says metals, they don't mean only the things you'd think of, the iron and the copper and the gold. They mean carbon too, and oxygen, and nitrogen, and just about everything heavier than helium, all lumped together under that one cozy, slightly inaccurate word. No chemist would call oxygen a metal, but the astronomers settled on the word a long time ago, for their own convenience, and it stuck the way a nickname sticks in a family long after anyone remembers why. So tonight, when I say metals, you can let go of the ordinary meaning and just think, gently, anything heavier than helium. The richer, more complicated ingredients that came later. And there's a companion word which is just as soft once you get used to it. Metallicity. It simply means how much of those heavier ingredients a place contains. A region with high metallicity has been worked over many times, enriched by generations of stars living and dying and scattering their contents. A region with low metallicity has been touched only lightly, and a region with no metallicity at all, or as close to none as we can measure, is a place where nothing has happened yet. A place still holding only the simple original ingredients, hydrogen and helium and a faint whisper of one more, all left over from the very first minutes of the universe, with nothing heavier ever added. That last kind of place is what makes this signal so unusual, because the pocket of gas where the helium glowed seems to have almost no metals at all. It seems to be holding only the original simple stuff, and in the universe today, that is, quite simply, impossible. There is nowhere near us, nowhere within an enormous distance, that hasn't been touched and seasoned and enriched by billions of years of stars. The contamination, if you can even call something so generous a contamination, is everywhere, and it cannot be undone. The only place you could ever find gas this clean is far back in the early universe, before the first stars had finished their work, or in some rare little pocket that the enrichment somehow never reached. And that, it seems, is exactly what this is. So now picture the two parts of this little region, side by side, because there were two. The scientists gave them plain little names, C1 and C2, and you don't need to keep track of which is which. What matters is the gentle contrast between them. One of them, the cleaner one, holds only the original ingredients, untouched, as pure as the morning of the universe, and the other, just beside it, holds a faint trace of the heavier things, a first whisper of metals, a sign that somewhere very near, a star had already lived its brief life and let its contents go. And the lovely thing, the thing that makes this signal so special, is that both of these are caught in the same little patch of light. The before and the after, sitting next to each other, a piece of the universe from just before the first stars had changed anything, and a piece from just after the very first change had begun, both captured in one quiet observation, in light that left them both 13 billion years ago. It's like coming across an old photograph that somehow shows both the dark room and the first soft flicker of the match being struck, both at once, in the same gentle frame. We'll spend more time with that idea tonight, slowly. The before and the after, the clean and the first faint seasoning. For now, let it rest in your mind, like two small stones sitting side by side on a windowsill, one pale and plain, one with the faintest streak of color running through it. And as we drift on, let me tell you how people first came to sort the stars into families, because it's a quiet little story, and it explains the slightly funny way these very first stars came to be named. It begins, as so many of these things do, with one person looking carefully at the sky and noticing something that others had overlooked. Back in the 1940s, an astronomer named Walter Bethe was studying our neighboring galaxy, the Great Spiral of Andromeda, and as he looked, he began to notice that the stars were not all the same. Some of them were young and hot and rich with those heavier ingredients. Others were old and cooler and held far fewer of them. He gathered them gently into two families. The young, rich ones he called Population 1. The old, poorer ones he called Population 2. And the numbering, you'll notice, follows the order in which we found them, not the order in which they came to be. The young rich stars were called the first population, simply because they were the ones all around us, easy to see, easy to study, the stars of our own familiar neighborhood. The older, poorer stars were the second, found further out, in the quieter outskirts, and the old gathered clusters, relics of an earlier time. But it didn't take long for people to realize that the story couldn't begin with Population 2, because even those old, poor stars held a little of the heavier ingredients, a small amount but not none, and something must have made that small amount. Something must have come before and done the first seasoning and made the first heavy elements out of nothing but the simple original stuff. There had to be an earlier family still, a first generation, stars that formed from completely pure material with nothing heavier than helium to start from, and that created, through their lives and their endings, the very first heavier ingredients the universe had ever known. And so that earliest family was named, and here is the small, charming tangle in it. They were named Population 3, the third name for the first family of all. Third to be imagined, first to exist. It's the kind of backward little naming that only makes sense once you know the order things were discovered in, and it has gently confused students for decades. But there's something rather sweet about it too. The very first stars in all of creation carry a name that says, quietly, we thought of these last, even though they came before everything. These Population 3 stars, the first generation, are what tonight's little signal seems to be about. For 50 years they were predicted, expected, written into the models, and never quite seen. The ghosts at the foundation of everything, necessary but invisible, and the small helium line near that faraway galaxy may be at long last a glimpse of their light. Let's slow down a little now and talk gently about why these first stars would have been so different from the stars we know. Because the reason is rather lovely, and it all comes down to one missing ingredient. Every star you have ever seen, every point of light in the night sky, every star anyone has ever named formed from gas that already held a little of those heavier ingredients. A trace of carbon, a trace of oxygen, a trace of iron mixed in with the hydrogen and helium. And those small traces, it turns out, do something quietly important when a star is being born. Let me describe it softly. A star begins as a great cloud of gas drifting in space. Gravity, patient and steady, begins to pull that cloud inward, gathering it together, drawing it slowly toward its own center. And as the gas is pulled together, it warms up. Anything squeezed grows warmer, the way the air in a bicycle pump grows warm under your hand. But that warmth pushes back. A warm gas wants to spread out, to resist the squeezing, and so the gathering can stall. The cloud just sits there, too warm to keep falling inward, puffed up and unsettled, and no star is born. What lets the cloud keep falling is its ability to cool itself down, to let some of that warmth escape, so the gathering can continue. And this is where those small traces of heavier ingredients do their quiet work. Carbon and oxygen, even in tiny amounts, are very good at carrying warmth away. They soak up the heat and then release it again as a soft glow of invisible light that slips out of the cloud and is gone. The cloud cools, the pushing back fades, gravity can keep gathering. And because a cooling cloud tends to break itself into many smaller pieces as it falls, you usually end up not with one enormous star, but with a whole scattered family of them. Some large, some middling, most of them rather small and modest. In the universe today, in fact, most of the stars being born are small, gentle, long-burning little stars, far smaller than our own sun. Now very softly take away those heavier ingredients. Go back to the early universe, before any star had ever lived and died, when the only things to make a star from were hydrogen and helium and that faint whisper of a third thing. These simple ingredients are not nearly so good at carrying warmth away. They try, a little, but they can only cool the gas so far, and then they stall, and the gas stays warmer than it otherwise would. The pushing back stays strong. The cloud cannot break itself into so many small pieces. Instead, it stays in a few large, heavy clumps, and each one of those clumps falls together into a single enormous star. And so the first stars were not like the modest little stars all around us today. They were giants. Where today's universe quietly prefers stars smaller than the sun, the early universe seems to have made stars tens of times the sun's mass, hundreds of times, perhaps in some cases close to 1,000 times. Vast, heavy, towering things, of a kind the universe simply does not build anymore. And a star that large is also, by its nature, extraordinarily hot. A star with 100 times the sun's mass has a surface far hotter than the sun's gentle glow. Push the mass higher still into the hundreds, and the surface temperature climbs past that 100,000-degree mark, into the realm where its light is fierce enough to strip helium bare, twice over exactly the way the helium in our little signal was stripped. So you see how it all begins to fit together softly, like pieces settling into place, a pocket of pure, original gas, a giant star forming from it, because the gas was too simple to cool and break apart, a surface so hot it strips helium down to nothing, and a faint line of helium light, sent out across 13 billion years, that says, when we read it, a great hot first-generation star once burned here. These were not gentle, slow-burning stars. They were brilliant beyond easy imagining. A single one of these first giants would have outshone our entire sun many millions of times over. A whole little cluster of them, glowing together in a pocket of pristine gas, would have lit that gas up like a lantern held inside a fog, its light pouring out far enough to touch the gas for many light years around. And that pouring out of light is, in the end, the very thing we catch as the little helium line. The lantern is long extinguished. The light still reaches us. But there is a price for being so large, and it's a quiet, almost tender price. The larger a star is, the shorter its life. It might seem that a bigger star with so much more fuel would last far longer. But the opposite is true. A great heavy star burns through its fuel furiously, recklessly, all at once, and so its life is brief. Our own sun is a modest, sensible star, and it will burn steadily for something like 10 billion years, a long, patient, unhurried life. A star 10 times its mass lives only a few tens of millions of years. A star 100 times its mass may last only a couple of million. A star approaching 1,000 times the sun's mass, if such a thing truly existed, would spend its fuel in perhaps 1,000,000 years or even less, a mere flicker against the long age of the universe. So these first stars were not steady, patient beacons that shone for ages. They were brief, brilliant flares. They ignited, they blazed with a heat and a light the universe has never repeated. And then, after only a short while, they came to their ends, and the way they ended is part of how everything that came after became possible. So, let me tell you about it gently, because even the endings in this story are soft to sit with once you understand them. For a certain range of these giant stars, neither too heavy nor too light, the ending was a complete and total letting go. Deep in the core of such a star, the conditions become so extreme that the light itself, the fierce radiation that had been holding the star up against its own weight, begins to quietly convert into tiny particles of matter. And as that light turns into matter, the support it had been providing fades. The core begins to fall inward. The falling makes it hotter, which makes more light turn into matter, which removes still more support, and so the whole thing tips into a runaway, gathering speed, until at last the entire star comes apart in a single great release. Not a partial ending, where a small dense remnant is left behind, but a complete one. The whole star, everything it had made in its brief life, scattered outward into space, leaving nothing at all behind. No core, no remnant, just an expanding, cooling cloud of new ingredients drifting out into a universe that had never contained them before. And for the very heaviest of these stars, heavier still than that, the ending was different and even quieter. There was no scattering at all. The collapse was so complete, so overwhelming, that the star simply fell all the way into itself and vanished, leaving behind a black hole, a small region of deep, gathered darkness where a giant star used to be. No flash, no scattering, just a great star and then a great silence, and a heaviness in space where the star had been. Both of these endings matter for the rest of the story, and we'll come back to the second one later, gently, because it connects to that black hole sitting quietly inside the faraway galaxy. But for now I want to stay with the first kind of ending, the scattering kind, because of what it scattered. To understand it, let me tell you, very softly, how the heavier ingredients are made in the first place. Deep inside a star, the simple hydrogen is slowly pressed together to make helium. This is what makes a star shine. When the hydrogen begins to run low, a large enough star presses the helium together too, and from helium it makes carbon. From carbon, with more pressing, it can make oxygen. From oxygen, in time, the heavier things still, on, each step needing more heat and more pressure than the last. Each step making a heavier ingredient, until the star arrives, at the very end of the chain, at iron. And iron, oddly and gently, is where the building stops. Iron will not give up energy when it's pressed together the way the lighter things will. It marks the quiet end of the line. So inside one of these giant first stars, in its brief and brilliant life, a whole ladder of new ingredients was being built, rung by rung, that had never existed in the universe before. Carbon, oxygen, the heavier things, all of it forming deep inside, in the dark, under enormous pressure, in a star made from nothing but the simplest original stuff. And then, when that star came to its scattering end, all of those newly made ingredients were released, flung gently outward, mixing into the pure gas around it. And in that moment, that quiet, enormous moment, the gas that had held only hydrogen and helium since the beginning of time held, for the very first time, a trace of something heavier, a first faint seasoning, the first carbon, the first oxygen, the first heavy ingredients the universe had ever known, drifting out into the dark. And that, you may remember, is exactly what the second little pocket near our faraway galaxy seems to show. The cleaner pocket holds only the original stuff, but the other pocket holds that faint first trace of the heavier ingredients. It is gas that has already received its first small gift from a nearby star that lived and ended. We are, it seems, looking right at the moment the seasoning began. The clean pocket is the universe before the first heavy ingredients existed. The faintly seasoned pocket is the universe just after they first appeared, and both are there, side by side, in the same little patch of ancient light. There's something quietly moving in that, I think, when you let it settle. The first time, in all of existence, that the universe held anything more than its two simplest ingredients. And it didn't happen with a fanfare. It happened in a small pocket of gas at the edge of a faraway galaxy, when one brief giant star let go of everything it had made. A single small beginning that would, in the end, lead to everything heavier that has ever existed anywhere. And here is a gentle thought to rest on for a moment, with no need to do anything with it. Every heavier ingredient that exists, everywhere, came from inside a star, the carbon in a pencil, the oxygen in a breath of air, the iron that makes blood red, the calcium that makes bones firm. Every atom of all of it, anywhere you might find it, was once made deep inside a star and then released when that star came to its end. And the very first stars ever to do this, the ones that began the whole long chain, seem to be the ones whose faint light a telescope has now caught. The first cooks, you might say, in a kitchen that had only just been built, scattering the first ingredients into a universe that would spend the next 13 billion years slowly turning those ingredients into worlds and oceans and living things, and eventually into you. But let's not rush ahead to that. Let it stay a soft and distant idea for now. We'll wander back toward it gently, much later, when the night is even quieter. For now, let's drift on to something else these first stars did, something that changed not what the universe was made of, but what it looked like. Because the first stars didn't only begin the chemistry of the cosmos, they also, in a sense, turned the lights on. To understand that, we have to go back very softly to the early universe, even before the first stars, and I'll tell it slowly, the way you might describe a long ago morning. In its very first moments, the universe was unimaginably hot and dense, a glowing fog of the smallest particles, all tangled up together. It was not dark, exactly. It glowed all over with its own warmth, but it was not clear, either. Light could not travel freely through it. A bit of light could move only a tiny distance before bumping into something, and scattering off in a new direction, the way a car's headlights can't really pierce a thick fog, but only fill it with a diffuse glow. The whole young universe was like that, bright but closed in, a glowing fog with no clear view through it. Then slowly, as the universe expanded, it cooled, the way a warm room cools when a window is opened on a winter night. And at a certain point, after a few 100,000 years, it had cooled just enough for the tangled particles to settle down and join together into calm, neutral atoms. And in that moment, the fog cleared. Suddenly, light could travel freely, on and on, across the open space without being scattered. The universe became transparent for the first time, and the light that was set free in that clearing moment is still traveling today, still washing gently across the whole sky, grown faint and cool over all the long ages since. We can still detect it, that very first light, the oldest light there is, a soft and even glow coming from every direction at once. There is something deeply peaceful in knowing it's still there, all around us, all the time, the gentle afterglow of the moment the universe first grew clear. But that clear, transparent universe was also, for a while, a dark one. The fog had lifted, but there were no stars yet. Nothing was shining. The first light from the clearing had spread out and faded, and no new light had taken its place. And so the universe entered a long, quiet stretch that astronomers call the Dark Ages. Hundreds of millions of years, transparent and still and dark, the gas drifting and slowly gathering, the first faint structures pulling themselves together under gravity, everything waiting, in the cool and the dark, for the first light to be lit. And then it was lit. The first stars ignited, those great hot giants we've been talking about all this while, and they began to pour out their fierce light. And that light was strong enough to do something to the dark, neutral gas all around them. It began to break the gas back apart again into its tangled, charged form, the way the warmth of a rising sun begins to lift the dew. This great slow change spreading out from the first stars and the first galaxies, gradually working its way across the whole cosmos, is what astronomers call the reionization of the universe. It was, in a soft sense, the universe turning its lights on for the second time. The first time was when the fog cleared, long before. The second time was when the first stars lit up, and their light reached out and changed the gas around them across enormous distances. And our little signal, you'll be glad to know, fits gently into exactly this part of the story. It comes from a time when this great turning on was underway, but not yet finished, when the first stars were just beginning their work of lighting up the dark, neutral gas. The first stars were not only the first cooks, making the first heavy ingredients. They may also have been among the great lamplighters, the ones whose light cleared the way so that, later, the light of distant galaxies could travel freely to us at all. Without them, in a sense, the universe would have stayed dim and closed in for far longer, and much of what we now see in the sky would have stayed hidden behind that neutral fog. So these brief, brilliant first stars left two great gifts behind them, even as they themselves vanished. They left the first heavier ingredients, scattered into the gas, the beginning of all later chemistry. And they helped clear the way so that light could move freely through the cosmos. They remade what the universe was made of, and they remade what could be seen. And then they were gone, every one of them, in their few brief million years, leaving only their light, traveling outward, to be caught much later by us. Now, I've been telling you all of this rather warmly, as though it were already settled, as though we knew for certain what that little helium line was. And the truth, the gentle and honest truth, is more careful than that. The scientists who found this signal have been very thoughtful, very patient, about not letting their hopes run ahead of what the data really shows. And I think it's worth spending a little quiet time with that carefulness, because there's something soothing in it, something steady and humble and kind. You see, before anyone could say this signal came from the first stars, they had to ask, gently and seriously, whether anything else might have made it instead, whether some more ordinary thing might be hiding behind it. And so they went through the other possibilities, one by one, the way you might check each window in a house at night, calmly, making sure each one is closed, before you let yourself settle down to sleep. One possibility was that black hole sitting inside the galaxy. Black holes, for all that they are dark themselves, can cause the gas around them to glow very brightly and very fiercely as it spirals inward, and that glow can include the same kind of fierce light that strips helium bare. So it was fair to ask, softly, whether the black hole, rather than any first stars, might be the source of the little helium line. But when the scientists looked closely, it didn't quite fit. The helium glow was stronger than the black hole should have produced at that distance. And the signal came from off to the side, out in that lonely pocket, not from the center of the galaxy where the black hole sits, which is an awkward place for a black hole's glow to be coming from. And some of the other signs that usually come along with a busy black hole simply weren't there. So while no one could rule the black hole out completely, it didn't settle comfortably over the data. It was like a coat that almost fit but pulled at the shoulders. You could put it on, but you wouldn't want to wear it. And so gently, it was set aside, not slammed shut, just quietly set aside as the less likely thing. There was another possibility, and this one is rather interesting, because at first glance it looked like a strong one. There is a kind of star, already known to us, already seen many times in the sky, that is genuinely enormous and genuinely fierce. These stars are so hot and so violent that they blow their own outer layers away, stripping themselves down until their searing inner selves are laid bare to space, glowing furiously across the invisible part of the rainbow. They are among the most extreme stars we know of in the universe as it is now, and they produce strong helium glow and great heat, much like the source of our little signal. So it was reasonable to wonder whether a cluster of these known fierce stars might be making the signal rather than some unseen first generation. But here too, when the scientists looked closely, it came apart, and it came apart cleanly, because these known fierce stars, for all their drama, always carry the heavier ingredients. Always. It is simply part of what they are. They are not young, pure, first-generation things. They are old, worked-over stars, late in their lives, that have already built up a whole horde of carbon and oxygen and nitrogen inside themselves. And that horde always shows up plainly in their light. There has never been one of these stars, anywhere, at any distance, that lacked those signs. And our little pocket of gas showed none of them. No carbon, no oxygen, no nitrogen, nothing but the clean, original simplicity. So to explain the signal with these known stars, you would have to imagine a brand new kind of star that nobody has ever seen. One that is just as fierce and just as hot as the known ones, but somehow holds no heavier ingredients at all. And that's a strange thing to invent. You'd be conjuring up an unknown object out of nothing, with no other evidence for it, only to avoid the simpler answer. Whereas the simpler answer, the first generation stars, had been predicted carefully for 50 years. Their expected light had been worked out in detail long ago, and what the telescope found matched that old prediction almost exactly. So, between inventing something new and unsupported and reaching for a long standing prediction that fits, the gentler, more sensible path is to lean toward the prediction, not as proof, but as the most natural reading of what was found. And that really is how the careful work goes. Not a single triumphant moment, but a patient closing of windows, the black hole set gently aside, the known fierce stars ruled out by their missing ingredients, one possibility after another considered fairly and then quietly let go, until what remained was the explanation that had been waiting in the old predictions all along. It is a slow, humble kind of progress, and there is something restful in it. Nobody shouting that they were right, just careful people, checking each window, making sure. And even after all those windows were checked, the scientists held on to one more piece of carefulness, the gentlest and the wisest of all. They reminded themselves that fitting a prediction is not the same as proving it, that a signal can match what you hoped for, and still, in the end, turn out to be something else. And they were honest about why that reminder mattered so much in this particular case. Because, you see, this telescope was built, in part, to find exactly this. The search for the first stars was written into its purpose from the very beginning, the size of its great mirror, the particular kind of light it was made to gather. Even the cold and distant spot it was sent to, all of these were chosen, in part, so that it might catch the faint light of the first generation. The people who designed it knew what they were hoping for. The people who chose where to point it knew. And the people who studied the data, who found the little helium line and understood what it might mean, had spent their whole careers learning the predictions about these first stars. So when they found something that matched those predictions, of course they recognized it. Of course it spoke to them. And that, the scientists gently acknowledged, is both the strength of the whole endeavor and its quiet danger. You cannot find a thing unless you first imagine what it might look like. You cannot build an instrument to catch a faint signal unless you already know which signal to listen for. Imagining comes first, then looking. That is how the whole patient practice works. And it works beautifully. But it also means that when you have spent years hoping for a particular thing, your mind is primed to see it, even in places where the picture is dim and uncertain. Not because anyone is careless, and not because anyone is anything but honest. Simply because the human mind is a pattern-finding thing, and it finds most easily the patterns it has been waiting for. The scientists know this about themselves, and I find that rather lovely. They tell each other gentle, cautionary stories to keep themselves humble, and I'll share two of them softly, because they're good stories to drift along with. The first is from long ago in the late 1960s. A young researcher named Jocelyn Bell Burnell was studying signals from a radio telescope when she noticed something odd, a faint pulse arriving with perfect clockwork regularity over and over from one fixed point in the sky. It was so regular, so precise, that for a little while no one was quite sure what could make such a thing naturally. And the team, half in jest, gave the signal a playful little nickname that hinted at the idea of a message from someone out there. Some distant intelligence sending a tidy, repeating beat across space. They didn't truly believe it. It was a gentle joke. But the joke showed how the mind reaches, in the face of something strange, toward the most extraordinary explanation. And in the end, the truth was natural after all. The pulses came from a small, dense, spinning star, sweeping a beam of energy around like the light of a lighthouse turning in the night, so that it seemed to flash each time the beam swept past. A beautiful, natural thing, not a message. But for a little while, What they wished for had colored how they spoke about what they'd found. The second story is more recent and a little more rueful, and the scientists tell it to one another as a reminder to stay humble. Some years ago, a team announced that they had found, in the oldest light of the universe, a faint pattern that would, if it were real, have been a glimpse of something extraordinary from the universe's very first instant. The announcement was enormous. There was celebration, there were headlines, there was talk of the highest honors. And then, some months later, a more careful look, with the help of another instrument, showed that the faint pattern had most likely come not from the early universe at all, but from ordinary dust drifting in our own galaxy, dust that happened to mimic the hoped-for signal closely enough to fool the first analysis. The result was gently and honestly withdrawn, and the people who had made the claim were not careless or foolish. They were among the very best at what they did, using the finest instruments, applying careful methods. They had simply been caught by a faint signal, a confusing source they had underestimated, and the strong, human wish to have found the thing their field had waited so long for. The scientists who found our little helium line keep these stories close. They know they are standing in much the same place, holding a faint signal from the very edge of what their telescope can see, a signal they had hoped and longed to find. And so they have been careful to say, plainly, that this is the strongest sign yet, the best candidate ever found, but not yet a settled certainty. The signal is real, that much is not in doubt, confirmed by a second faint line that rules out any simple trick of the instrument. The reading of it matches the old predictions. The other explanations have been gently set aside. But to move from the strongest candidate to a thing that is truly settled, they need one more thing, and they say so honestly. They need to find it again, somewhere else, near another galaxy, at another distance, in another patch of ancient sky, caught by another set of careful eyes. If the first stars really did form in these little pristine pockets, then there should be more of these pockets out there, more places where the same clean helium glow appears, untouched by the heavier ingredients. Finding even one more would make the whole picture far stronger. Finding several would all but settle it. And so the work goes on, patient and unhurried, the search continuing for more of these faint, clean little signals, scattered across the early sky. There's something deeply restful in that, I think. The willingness to wait, the refusal to declare victory before the universe has shown its hand a second time. The scientists are not in a hurry. They have waited 50 years already. They can wait a little longer and look a little more, and let the answer arrive in its own time, the way that faraway light arrived in its own time after 13 billion patient years. Let's drift gently now back toward the telescope itself, because it deserves a little quiet appreciation, and because there's something soothing in the sheer patience of how it came to be. This machine was not built quickly. It was dreamed up long ago, decades ago, and then slowly designed and argued over and refined and built piece by careful piece over many more years than anyone first expected. There were setbacks. There were long delays. There were times when it seemed it might never fly at all. And through all of that, people kept working on it, patiently, the way you might tend a garden over many seasons without yet seeing it bloom. Its great mirror is wide and golden, made of many smaller pieces fitted together, coated in a thin, gleaming layer of gold, so that it might catch the faintest, oldest light as gently and completely as possible. And to gather such faint light, it could not stay near the warm, bright bustle of the earth. It had to be carried far away, out past the moon, to a cold and quiet and remarkably stable spot in space, more than 1,000,000 miles from home, where it could sit in the dark and the cold, and stay very, very still, and listen. To get it there, it had to be folded up small, like a great piece of origami, tucked into the top of a rocket, and then sent up and out, and then, far from any helping hand, unfolded again, slowly and carefully, all on its own, in the silence of deep space. Hundreds of small steps, each one of which had to go right, with no chance to fix it if it went wrong, and one by one, in the quiet, each step went right. The mirror opened, the great shade that keeps it cool unfurled. The instruments cooled down into their proper deep chill, and the telescope drifted to its distant resting place and settled in, and turned its golden eye toward the dark, and began, gently, to gather light. It was sent up on a winter morning around the holidays, a quiet kind of gift to everyone who had waited so long for it, and it reached its far resting place a month later, and after a little while longer, once it had cooled and steadied and its eye had been carefully focused, it began its real work. And within only a few years of that work, among everything else it gathered, it caught that one faint little line of helium light from the edge of a faraway galaxy, the very kind of signal it had, in part, been built to find. There is something gently satisfying in that. A machine made over decades, with so much patience and so much hope, doing quietly the very thing it was made to do. Now, I promised we'd return to that black hole sitting inside the faraway galaxy, and this feels like the right soft moment to do it, because it ties back to those first stars in a way I find rather beautiful. You'll remember that the very heaviest of those first giant stars didn't scatter themselves at all when they ended. They simply fell inward, completely, all at once, and left behind a black hole where the star had been. And because those first stars were so very large to begin with, the black holes they left behind would have been large too. Not the small, modest black holes left by the ordinary stars of today, but heavier ones, hundreds of times the mass of our sun, right from the start. And that turns out to be quite useful in a gentle way for solving a small puzzle that has been quietly troubling astronomers. The puzzle is this: when we look out at the early universe, we keep finding black holes that are already enormous, already vastly heavy, far heavier than seems easy to explain so soon after the beginning. Black holes usually grow slowly, gathering mass over long ages, the way a snowball grows as it rolls. To become truly enormous takes a great deal of time. And yet there they are, these great heavy black holes, already grown when the universe was still very young. The black hole inside our faraway galaxy is one of them, surprisingly large for such an early time. How did they grow so big, so fast? One gentle answer is that they didn't have to start small. If the very first stars left behind black holes that were already fairly heavy, then those black holes had a great head start. They didn't have to begin as tiny things and slowly build themselves up over ages they didn't have. They began already substantial, already several hundred times the sun's mass, and from such a starting point, growing into the great heavy black holes we see becomes far easier, far more comfortable within the time the universe allows. The first stars, in other words, may have planted the seeds of the great black holes that now sit at the hearts of galaxies. Some of the first stars scattered the seeds of all later chemistry, and others, the very heaviest, may have planted the seeds of the black holes. Two quiet legacies from one brief generation of giants, both still with us long after the giants themselves are gone. I find that a peaceful thought, somehow, that nothing was wasted. That even the stars which ended in silence, leaving no scattered ingredients behind, still left something, a heavy seed in the dark that would grow, over ages, into something that shapes whole galaxies. Nothing was wasted. Everything led, in its own slow way, to what came next. And that brings us, gently, toward the quietest and most personal part of tonight's wandering, the part where all of this distant ancient business comes drifting, ever so softly, all the way back home to you. Let me lead into it slowly, with no weight on it, because it isn't a thing to be startled by. It's a thing to rest in. We've talked about how the heavier ingredients, everything past hydrogen and helium, were all made inside stars, and then scattered out, generation after generation, into the gas of the universe. We've talked about how the very first stars began that whole long process, taking pure, simple gas and turning it, through their lives and their endings, into the first carbon, the first oxygen, the first of the heavier things, and then how those first ingredients mixed into the gas, and later stars formed from that slightly richer gas, and added more, and then those scattered too, and on, generation after generation, each one passing along a little more, each one seasoning the gas a little further, over 13 billion patient years. And every one of those ingredients eventually settled somewhere. Some of it drifted together into clouds, and the clouds collapsed into new stars, and around some of those stars, the leftover material gathered into worlds. Our own sun formed this way, from gas that had already been enriched by countless earlier stars. And around our sun, from the same enriched material, the earth formed, and everything on it. And from the material of the earth, in time, living things formed. And living things are made, in the end, of those same heavier ingredients, the carbon and oxygen and the rest, the very ingredients that were made long ago inside stars. So when you breathe, the oxygen you take in was made inside a star. When you feel the calcium that gives your bones their firmness, that calcium was made inside a star. The carbon woven all through you, the iron that warms the color of your blood, all of it was forged in the hearts of stars and scattered out into space long before the earth existed and gathered over ages into you. You are made of the scattered insides of stars that lived and ended long ago. And the very first of those stars, the ones that began the whole chain, the ones whose faint helium light a telescope may now have caught, are part of your story too. Not as a metaphor, as a quiet, literal thread running all the way back from you through generation after generation of stars to that first small pocket of pure gas at the edge of a faraway galaxy, where the first giants burned and ended and let go of the first heavier ingredients the universe had ever known. The little signal and the atoms in you are connected by a long, unbroken line. The clean pocket of gas is the universe before any of your ingredients existed. The faintly seasoned pocket beside it is the universe in the first moment after the very first of those ingredients began to be made. And the gentle gap between them, captured in a single patch of ancient light, is, in a sense, the moment the universe first became capable of, someday very far down the line, making something like you. There's no need to feel small under that thought, and no need to feel large. You can just let it be what it is, a soft and steady fact, like the weight of a blanket. You are part of a very long, very patient story. The story began far away and long ago, in places we can barely see. It moved slowly through ages and ages, scattering and scattering again, asking nothing, hurrying nowhere. And here you are, at the gentle far end of it, lying in the quiet, drifting towards sleep, made of the very oldest things there are. And the people who study all this, when they sit with it, sometimes feel a kind of quiet wonder at how fragile the evidence is, and yet how far it reaches. The most important objects in the whole long story, the very first stars, the ones that began the chemistry of everything, are also the hardest of all to see. They are long gone, every one of them, vanished within the universe's first stretch of years. They left no survivors. There are no first stars still burning somewhere that we might point a telescope at and study at our leisure. They lived their brief, brilliant lives, and they ended, and that was that. What remains of them is only light, set loose long ago, traveling ever since, growing fainter and softer and redder with each passing age, until a thin trace of it arrives at last at a small machine in the cold and the dark. So everything we will ever know about those first stars, we will have to gather indirectly, gently, from clues, from the faint light they left behind, from the patterns in the oldest surviving stars in our own galaxy, ancient stars that formed from gas only lightly touched by the first generation, and that carry in them, like an inherited trait, faint hints of what their unseen ancestors must have been. From careful models and simulations built from the physics we trust, that try to reconstruct what those first stars were like, and how they lived and how they ended. And now, perhaps, from this one faint line of helium light, the closest we may ever come to catching the first stars in the act of shining, it is a little like the work of those who study the deep past here on Earth, who reconstruct whole vanished creatures from a few fragments of bone, or whole lost ways of life from a few broken pieces of pottery. Building a large and careful picture from small surviving pieces is not new. People have always done it patiently with whatever the past has left behind. What is remarkable here is only the scale of it, the way we are reaching, from a small machine near the Earth, all the way back to the very first light, and building, from the faintest of traces, a picture of how everything began. It is a gentle, humble kind of knowledge. It is built from fragments, and it is, even so, real knowledge, growing a little fuller and a little surer with each careful new look, and the looking will go on. The same telescope that caught this signal has years of quiet work ahead of it, and it can keep searching, patch by patch of ancient sky, for more of these clean little pockets of helium light near other early galaxies. It can also return to this very pocket and study it more closely, more slowly, gathering its faint light for longer, looking at it from more angles, testing whether the clean, pristine reading truly holds up under a longer and more patient gaze. And beyond this one telescope, others are being built, here on the ground, that will join the search in time. Great new telescopes, with mirrors far larger still, are rising slowly in quiet, dry, high places where the air is calm and the sky is clear. One is being built in a high desert, with a mirror many times wider than the one now floating in space. Others are planned for other mountaintops, each one an enormous, patient effort, taking many years to build. And when they are finished, they will work alongside the telescope in space, each seeing in its own way, each able to study these ancient, faraway things that today we can barely make out. Between them, the eye in the cold dark of space, and the great new eyes on the quiet mountains of Earth, they may be able to answer the question that still hangs gently open. Whether this one little signal was a rare and lonely thing, or the first glimpse of something common, scattered all through the early universe, waiting to be found again. And if that question is answered, if the first stars are truly confirmed at last, then the work does not end. It only changes and deepens, because then the question stops being whether they existed and becomes, instead, what they were truly like. How heavy they really were, how long they really burned. Whether they formed alone, single giants kindling in the dark, or together, in little clusters, the way the two pockets near our faraway galaxy seem so gently to suggest. How many ended by scattering, and how many ended in silence and became black holes? Each of those questions is large enough to keep careful people busy for a long, long time. The finding of the first stars, if it holds, would not be the end of the story. It would be the quiet turning of a page, from the long search to the long, patient study of what was found. There is something I find deeply restful in all of this, and I'll offer it softly as we begin to let the night grow quieter. For most of the long history of people, the question of where everything came from, where we came from, what the world is made of, and how it began, was answered with stories. Beautiful stories, every culture had its own, told around fires and passed down through generations, each one reaching toward the same gentle wonder. How did all of this begin? Those stories were not science, but they came from the very same place in us, the same quiet looking up at the sky and wondering. And now, for the first time, we can begin to answer a small piece of that ancient question in a new way. Not by replacing the wonder, but by following it outward, patiently, through faint light from the edge of time. We can draw a soft, unbroken line, from a small machine floating in the dark, all the way back to a pocket of pure gas at the edge of one of the first galaxies, where the first stars burned and ended, long, long ago. And along that line runs everything, every later star, every scattering of new ingredients, Every cloud that gathered, every world that formed, every ocean, every living thing, all of it, strung along that single patient line, leading at last to here, to now, to you, lying quietly in the dark. The universe tucked its oldest secret away in light, faint and stretched and far. It sent that light traveling for 13 billion years through slowly widening space. And we built a small machine and carried it far from home and pointed it at a tiny patch of ancient sky. And there, in a thin spike of helium light, we found what may be the first stars of all. The long search may be over, or it may be only just beginning. Either way, there is no hurry now. The light has already traveled all that way. It has already arrived. There is nothing left to do tonight but rest with the wonder of it. And so let the whole vast story grow soft and distant now, the way the lights of a far-off town grow soft when you watch them from a hilltop at the end of the day. The first stars burned long ago, and burned only briefly, and then they let go of everything they were. And that letting go became, in time, the gas and the worlds and the living things and the quiet of this very moment. They gave everything away gently and asked for nothing, and their faint light is still arriving, even now, even as you drift. There is nothing you need to carry from any of this, not the names, not the numbers, not the distances. You can let all of it settle to the floor of your mind like dust settling in a still room. The only thing worth keeping, and even this you can hold loosely, is the soft feeling of it. That you are part of something very old and very patient. That the things you are made of have been on a long, slow journey, and that the journey has brought them, at last here, to rest in you, in the dark, at the end of the day. Let your breathing slow. Let it grow soft and even, the way the oldest light is soft and even across the whole sky. There is nothing to watch for, nothing to wait for. The story will keep itself. The light will keep arriving, whether or not anyone is looking, and the great patient universe will go on being patient, while you let go of the day and let go of the words, and drift down gently into sleep. Rest now. The stars have been burning for a very long time, and they will go on without you keeping watch. The first light traveled 13 billion years to reach a small machine in the cold and the dark, and it asked nothing of you, so you can set everything down. You can let the quiet come up around you like a soft tide. There is all the time in the world, and more, far more, than you could ever need. Drift now, softly. The way light drifts across the dark, in no hurry, going nowhere in particular, content simply to travel, let go and rest.